Okay, let's continue. The clip is missing, so but I can get by. Did we go through this? Did we go through this example? We have joint probability mass function of x and y, and it is given in this way. And what we are asked to do is to check whether x and y are independent. Did I go through this or no? All right. Thanks. And how about this? No, right? Oh, okay. Oh, okay. Now I remember. I just give you the definition. Basically, so, okay, all the while we have been talking about two random variables that are jointly distributed. But this is, there is a more general formulations. The more general formulations is that I have n random variables, and they are all jointly distributed, like, for example, height, age, and then year of educations, and there are some more. So this is really the real situations. In many real, in a lot of nowadays data, this is what we call a very high dimensional random variables, that kind of situations. For example, if you this is your portfolio in your investment, so n might you are investing on n stocks or n something like investment instruments. So each of the instrument will be distributed or jointly distributed. So for example, this is stock 1, stock 2, and then maybe bond 3, and so on and so forth. And so and so you are monitoring how they jointly change. One of the things is that so we have the marginal. Now there are many marginals, but I don't want to get into the detail. So suppose you have fxy set, and then xy set. Oh, okay. Oh, hi. I'm sorry. The clip is gone.
Okay.
Yeah, I can get by now. But yeah.
Okay.
Because sometimes if it doesn't.
Okay.
Oh yeah, the PC.
Hello, my test.
Wow. I'm getting a prize. Okay. Yeah, thank you.
Yeah.
So I have to off this.
Yeah, off it is.
So this will be captured in the webcast.
Yes.
Okay,
Yes.
thank you. Okay, so let's say I have this, and then the assumption is that these are discrete. All of them are discrete. And so in order to get the marginal of this, you will need to sum over all the y, all the z. Whereas your x is fixed, the x corresponds to the same x here. Okay, so this is the definition. So you basically sum up everything that is the other things, all right? Now, so as a result, the complications in these situations is there are more than one type of marginals. There are actually, now of course you have this, you also have this, but you also have this. So basically you sum over only the effect of z. And now the xy is the same as here, but now you have a set here, all right? So there are many types of marginal distributions, but what in the slide is, this is the one-dimensional marginal. So you can think of it as the original problem is 3-dimensional, so you will have 2-dimensional marginals. There are 3 of them, xy, xz, and then yz. And you also have 3 one-dimensional marginal. So there are many types of marginals here. Now, the definition of the independence is a very neat formula here. So this would be just all the one-dimensional random variables, all the one-dimensional marginals. And so if the product of this give you back the joint probability mass function, then the random variables all are independent, all right? A question raised was at the end of last lecture was why would there is such a difference between events and all this. The events is a single event per se, so there is no other things to help. But whereas in when you define the marginals, the fact that you get this is coming from summing over this kind of things. So there is an inherent difference in there. So okay, so let's illustrate some examples. Now, a caution here is that all the x, the values here has to be, this is an equal sign for all choices of this. So now even though I have one simple equality to check, in fact, there are many of them. You have to check through all the small x1, small x2, and small xn. So if there are, say, 10 small x1 and 10 small x2 and 10 for also xn, so you actually have to test 10 to the power n of them. But of course, very often you have general expressions, and so you basically check the expressions, whether the expressions in x1 up to xn on the left-hand side is the same expressions that you have in x1 up to xn on the right-hand side. So you don't really check everything. All right? Okay, so this is the problem here. An example, I have 3 balls that are randomly selected from an urn containing 3 red, 4 white, and 5 blue balls. If we let R and W, okay, by the way, I forgot one thing. One thing to remind you, I think this is pretty standard among Singapore students. Please bring an identity card that with your photograph on it. Especially many of you don't come to class. I'm talking to someone who's watching, all right? And I don't even know whether you are my student or not my student. So, okay. I can recognize you, but that would also mean you can't find someone to pretend to be you, all right? So, okay, so suppose there are 3 balls that are randomly selected from an urn containing 3 red, 4 white, and 5 blue balls. I think we have dealt with this a little bit earlier. We let R and W denote the number of red and white balls because there are 3 colors, so I only need to track 2 colors. All right, because the remaining part would be the remaining color. Okay, so I wanted to find out whether R and W are independent. It's unlikely, all right? The heuristic here, or the intuition behind is, if you have independent means that the number of red ball that you selected will be more or less independent of the white ball that you will have, okay? Now, but this is unlikely to be true, because if you have a lot of red balls, that would preclude the white balls, all right? So we can see that, okay? But we want to go by definitions. I suppose we have done this before, right? This table, right? You're even more forgetful than I am, so. Okay, now, if you don't remember, then it'll be an exercise, all right? So, our starting point is this table. Now, once you have this table, okay, this part, then you can work out the marginals by adding things up. So, in this example, I think the guy who prepared the lecture notes purposely not to simplify the fractions. so that make the addition easier. So here would be just 84 over 220, and so on and so forth here. Now, once you have this, then you need to check whether they are independent. The random variable red, number of reds, and number of white. Of course, you can check by multiplying this number and then multiplying this number together and check whether you get this, all right? So this is one way, and then you check every entry here. But there is a much faster way for this particular problem that you have something like 0 here. Okay, look at this entry, let's say for the sake of here. Look at this entry 0. Now this entry 0 cannot come from the product of their corresponding marginals, because the corresponding marginal would be positive here, and this is positive. So when you multiply two positive numbers, you can't get a 0. So once you have some 0 in the table, the first thing you wanted to check are those entries, because you don't even need to do the calculation. All you need to check is whether the corresponding marginals, the row and the column specifying this particular entry, are they all positive? Okay, so they are not. And this is exactly what our intuition was. If we have a lot of red, let's say I have 3 reds, then definitely you can't have any white. I mean, even one is not feasible. Okay, so this really corresponds to our intuition of independence, because knowing how many red balls you have, actually the number of white balls will be affected. All right. Okay, so I guess we'll just go over this quickly. All right. Okay, so this is the trick here. So pick an entry in the table that is 0, and then and knowing that the marginals are not. All right. Also, now of course, if the question itself is just asking us whether they are independent, we don't really need to do so much work. All right, we don't need to do the entire table. All we need to do is to check that it is not true for some choices of number here and some choices here. So the choice here is exactly choose something that it is impossible to achieve, because you are now picking up 4 balls. But since the story is you only choose 3 balls, so no way you can get 2 red and 2 white. So the left-hand side is 0. But then now we need to argue that whether this is positive, this is positive. All right. So that might be a simpler, a more direct way than constructing the table and all this. So if all we care is to check whether R and W are dependent. Okay, the joint probability mass function of xy is this. So the table does not include the column totals and the row totals. So all you have is these 6 numbers. And I have it here, all right? Okay, and the way that we are doing it is as a preview when we are doing chi-square tests. I mean, probably in chapter 6 or even in chapter 7. One of the hypothesis testing is whether the random variables are independent, all right? So, or there is no associations. Very often we are interested in, say, whether if I say gender, okay, and then whether the kind of education's distribution, are they independent of the gender? So anyway, once you have this table, you can work this out. Okay, and then in fact, if we didn't have enough space here, so in the chi-square test, this is your 0.1 here, and so you multiply 0.4 and 0.25, so this is the original number, but this is the multiplication of this and this. And so you will have 0.15 here. And so this is also 0.15. All right. Now, for those who have taken some chi-square test, this is your observed frequency, relative frequency. And then this will be in that particular test, this is your expected frequency. So we will change it to frequency later on. And basically, we take the difference of this and then square them and divide it by the expected frequency. So this is very, very parallel to that. All right, so and this is 0.2 and this is 0.1. All right, so you multiply 0.4 and 0.5 and sure enough you get 0.2 and then 0.6 and 0.5, so you get 0.3, all right, and 0.4, and then this will be 0.1. So after we checked that, we found that all the numbers tally, all right. So this is where you have to check basically 6 equations. Now, in fact, I mean, of course, this is, very straightforward to do it. One way is that once you have a table, and if you are okay with Excel, then you can construct another table based on this, or the marginals, and then multiply the corresponding entries. And so you will have a new table. All you need is to check whether this table and the black table here, are they the same, all right? Now, of course, for calculations, it's not much work more. All you need is to check 5. Because we know they all add up to 1, and if 5 of them agree, the last one have to agree. But this is just something very minor. So this is echoed back what I was saying earlier. The expression that you are going to check seems innocent, only one equation here. But in fact, you actually have to check, especially for discrete random variable, all of them, all the possible choices. So n equal to 2 in that particular example, and then x1 has 2 values, and then x2 has 3 values. So I have to check 6 of them. So the condition for independence is very neatly okay. I think have we defined that not independent? Okay. So I think we should add in a definition saying that x1 up to xn are dependent if they are not independent. So it's a dichotomy. You have only 2 categories. One, either they are independent or they are not independent. Okay. So in fact, I think this way of checking is a little bit, you have to write many lines, but if you are going back to the table, and I think this is quite easy to do. Okay. All right. So another example, x and y, they are discrete, and so you have a 3 by 3 tables. And as a result, you want to check whether they are independent or not. From the marginals, you can find out it has a neat equation, expressions, and so on. Okay, so you can check that they are independent. All right. But I want to make a remark because I seem to receive a few emails asking something. I didn't quite notice it, that it is a concern. Some of you pointed out I think maybe in the last week's solution, when we give you the solution of a discrete situation, sometimes we give you a table and sometimes we give you an expressions. Now, either way would be fine, all right? But imagine if you don't use a table use a function form, then you will have 7 lines. The first line would be when x equal to 2, y equal to 1, then your joint distribution, your joint probability mass function is equal to 0.1. And then another one would be x equal to 2, y equal to 3, and then would be 0.2. So the functional expressions here will be very tedious. The 7th line would be otherwise. I mean, when x is not 2 or 4, or y is not 1, 3, or 5, then the f value here would be 0. So it is just a little bit more complicated. But so a table would be a better way. But here, why would it be easier? Because it has general expressions and expressions that generate the entries of the table. Of course, you can still resort to the table, but this is, I think, to me, is more informative. It says that the entries come from a formula, and that formula applies to every entry. So, I mean, this is giving you further understanding of the situations, all right? And so you have this, and they are independent. Okay, so maybe to conclude whether you want to express your, in the discrete case, whether you want to express your either the probability mass function or even a joint or whatever, you can write it as a function form like this, all right? But you have to define it for all the x and all the y here. So you really need this line, 0 otherwise. But if you can also do it for a table, all right? There is no preference, but of course, I mean, for better understanding, having a general expression is, is more informative than just a bunch of numbers. Okay, another example. Now this is the usual way to go about it. Finding joint distribution usually is very difficult from real life problem. But if I have some justifications that the random variables themselves are independent, then I will be able to find the joint probability density function much easier. I don't know whether you have experience in numerical integration. If you only do one dimension, say suppose you break the interval into 10 parts and then approximate your integral by 10 numbers. But if you are in 2 dimensions, in order to achieve more or less the same accuracy, now you have to use 10 for one direction and 10 for the other direction. So you are talking about 100 points. So that would be difficult. When you are in higher dimension, to know the joint PDF is very difficult. I mean, unless you have some mathematical model. If you are entirely empirical, it means you have to sample in many, many places in order to know something about it. But if you have independence, all you need is just one guy, X here, and then the other guy here. So back to the example, if I only use 10 points here, and then I only use 10 points, the approximation, can be reasonably good. So that means I actually need to look at 20 points. I don't need to look at 100 points, 10 by 10 versus 10 plus 10, right? So the advantage of having independence from other sources, and then and all you need to know is the marginal, all right? So once you have the marginal, then this is guaranteed. The joint is actually given by the product of the 2 marginals. And so as a result, we can just simply multiply them, and so I will have this, all right? So this is okay, all right? Is that all right? And here, the question, example 7 asks about x and y are independent. Now, what is coming in the few slides would be hard work. First of all, I have to find the marginal, and then I have to check. So this is what is being done. Now, so this is the work here. But in fact, I will tell you something a little bit faster, and that is called factorization theorem. If you have a joint distribution probability density function, and if you have a function g of x only in x alone, and then a function h of y, you don't even need to take care whether g is always positive. G can be negative, and then h can be negative or positive. But of course, the product would be non-negative, right? Because suppose this is true. Okay, suppose this is true for all x and y. Okay, I have this factorization, and that is why it's called a factorization theorem, which is true here. Then x and y are independent. All right. So this is a very useful situation, because if you go back and look at this, here, for the example 7, fxy equal to x e to the power minus x plus y is actually this. Otherwise, right? And so if I think of x times e to the power minus x e to the power minus y. Yeah. Hey? Okay. So so we are here, example 7. This is the expression here. And so I can just group all the x on one side. So this will be my g of x. This will be my h of y. And so, and also it is in a square form. So my g of x will be x e minus x, x positive, 0 otherwise. And then my h of y would be e to the power minus y, y positive, and 0 otherwise. All right? So I don't really care. I don't even need to guarantee g and h has to be a density function. If you want, just for the fun of it, you can give a minus sign to it. Because I didn't say that g and h has to be density functions, as long as any function, all right, such that the product of them will give you back this. And the only thing you need to check, this is true for all xy, all right? And so, but you can see the way I added in the negative sign will be always in pair, because I need to compensate back in order to have it equal. So it doesn't really matter. So of course, why do funny things when you can just do ordinary things, right? So this is a factorization theorem saying that if you are able to factorize the joint PDF into product of functions, each of them involve one x1, the other involve x2, and then the other is xn. So so this is it, all right? But of course, you can go through the calculations here, which is not too difficult, but it takes a little bit of effort to do so, all right? So x and y are independent. Okay, example 8 is a negative example, giving you the fact that not all joint probability density functions will correspond to independence. Now, think of the following. If you are looking at the marginal of x, so you'll be integrating over x. But when you are restricting yourself from 0 to 1, so your vertical line would pass through this orange triangle, meaning that when you do the integration, you will the integrand, after you do the integration, it will be positive. And similarly, if you do it horizontally and the horizontal line pass through the orange triangle, the marginal of y will be positive. This is corresponding when you are adding things on the table. And you have something positive here, so you will pick up something. So what it means is that the marginal along this any point here, corresponding to the row total and the column total, it would be positive, the two marginals. But whereas here, if you pick up a point somewhere here, now the joint density is 0 because it is outside the orange color. But yet, your vertical line and your horizontal line will pass through the orange triangle. And so you will pick up something positive for the marginal of y and also the marginal of x. So what it means is now your fxx at that point is positive and fyy is positive at that point. So again, when you multiply them, it would be positive on your right-hand side. But since I picked the xy is in this white triangle, the joint probability density function is 0. So both sides can't equal, all right? So as a result, they are not independent. So then we just say that x and y are dependent. Okay, so this is just doing the math, all right? In fact, if you are out to prove that it is not independent, all you need is to exhibit one pair xy so that the joint density function is not equal to the product of the marginal. That's all you need, okay? So all you need is just one bad apple to spoil the whole thing, all right? So you don't really need to do that. Of course, now this is just a sort of taking a chance, but all right, so here in the lecture notes, we really work it out more so because of as an exercise of your integrations. So we have that, all right? So I think we should say y equal to x here to make sure there is no misunderstanding in the upper limit after I substitute it in, all right? Because x is held fixed for the time being. Y is only changing. Y is the one that you are integrating. All right, and we do the same thing here. So it is, I mean, you really need to sit down and do the work. So it is not something that you can watch television and then do it. All right, and so as a result, you have this. All right. Okay, so this is the trick here. To show that it is not independent, the trick is to pick a point so that it lies in the rectangle, but is in the right triangle. All right, and so as a result, if it is in the right square, this will be positive. This will be positive. But if you purposely pick your xy in the white triangle, this will be 0. So the two can't be equal. And actually, we have chosen more than one pair of xy. I mean, it's the entire white triangle will do the trick here. So it's the entire patch that they are not equal. All right. So this is this. This is the 0.6 and 0.8. So this is lying on top of the y equal to x line in the triangle. Okay, so x and y are not independent. So or you can say x and y are dependent. All right, because I only have two classifications, either independent or not independent. Okay, so now this is another example. So now it is the region is a square, so I don't have the old trick to help me. Okay, so I have to do the work here, and this, and so you have to verify whether this is the case. Now to verify this, you have two expressions in y. In the previous slide, you also have two expressions in x. So when you multiply them, you should have four expressions, all right? Because you pick one of the two and one of the two. But because you have a 0 here and a 0 here, if you pick this second option, whatever it is, it will be 0. And then here, the 0 here, whatever option it is. So when you multiply them, there is reduced to only two expressions, all right? So you can check that. All right. Again, is repeating this. It's just mathematics here. All right. So you do the work here, and then you find that this is not even true for any x and y. So okay. Actually, we don't need to have this for all x, y, at least for some x and some y, that would be enough. All right, so x and y are not independent. Okay, so I guess I wanted to have a break here because we'll be starting a new topic on expectations and covariance. Okay. Okay, so do come back at 10:45. Okay. An interesting question was brought up during the break. So let's go back to here. Okay. The work has been done, but let's say I'm trying to illustrate it with the factorization thing that I taught you about. There is this here. So now, of course, if you draw the table, I mean, x is 1, 2, 3, y is 1, 2, 3. Then you use this formula to fill in the entry. Then you work out the marginal, and then it will work. All right. But here there is another way to say this. I don't know whether it was worked out in the on slide 465, but there is no harm to do it here. So I'm interested in calculating this, but we restrict x is equal to 1, 2, 3. So by definition, we have to add up all the y. Small x is fixed, and then my y is changing. So I'm actually adding up all the different y. Okay, and so, but because of the nature of the problem, it is x1, and xy is x2, and then this is x3. And we were told that it is x times y over 36. So this is x, this is 2x, this is 3x. So as a result, this is x over 6. All right, so that is how this is, can be done. Or of course, if you have a table, then it would be the same. All right. Another thing here is I can still use a factorization argument because it was written as x times y, and also the range is in this way. This is sort of like a rectangle in that situations. So I can think of it as a multiplication of x over 36 times y. So I group everything in x on one side, and I group everything in y on another side. So this is, I think, in your differential equation or whatever, in some other module, this is called variable separations. So if you are able to separate the variables on one side, and then another variable on one, so they are not twisted. All right. For example, if you have something like sine xy, then you can't put x all on one side, put y all on one side. They come together. All right. So if you have this, then of course I can see that it is independent. All right. Okay. So similarly, there are a number of such situations. Here I can group everything here. Now, of course, this is not a density function because the integration over just x itself will be equal to 2, not equal to 1. But in the factorization theorem I mentioned, you don't need it to be a density function. All right, so that's okay. Of course, a better way is to put the 2 together with the y here. So you write as e to the power minus x times 2 times e to the power minus 2y, and 2e to the power minus 2y is a density function in y, and then this is in x. But it is not important. And again, you can do so. X times e to the power minus x on one side, and then the other is e to the power minus y. So you can see, you can save quite a bit of calculations. And here, I think I've spent some time in explaining. And also, no way you can separate them, all right, as a product, not as, okay. Okay. Similarly, here, now this is a rectangle. Okay, so I don't have holes. And then I can put x on one side, on the left, on my first factor, and then the other factor is 1 plus y over 3. And so I can see that it is x and y are independent, all right? Okay, and now here it is not clear because I can't factorize them, all right? Because I can't factorize them as products, okay? Okay, we wanted to, the expectation will be very similar to what we have done in one variable, in one dimension. If you are having two random variables, then you will need their joint probability mass function if both of them are discrete, or their joint probability density function if both of them are continuous. And so you will do a double integral over there. And for discrete, you will do a double sum, all right? So you will see, actually, if you are talking about 10 dimensions, then the integration can be horrendous, all right? So it's in 10 dimensions, so it is life, all right? All right, so in discrete case, this is how it is defined. So maybe I want to parallel this with what you have learned in one dimension. So this is actually a generalization. So in the discrete case, this is g of x times the this, all right? And here, if you have a 2, then now, of course, you have to sum over x, sum over y. All right, so this is it. Now, this is one way of writing it, but some textbook or book that are tend to be on the more advanced level we'll just write it this way. Okay. So this is just a shorthand notation for this. And this is fairly convenient because if you have, say, you have 100 of them, x1 up to x100, you are not going to write 100 summation sign. I mean, so there is an advantage here. But this is only a shorthand advantage. The actual word is still the same. All right. Okay, and now for continuous case, so you will be doing something like this. All right, and for continuous case, now you have to do it this way. Okay, and you have a choice whether you want to integrate x first, y later, or y first, x later. It's the same, all right, under the fact that it is absolutely integrable, all right, but probably you haven't heard of this term yet. So the order is not important, all right. When it is, you have a finite number. All right. Okay, so this is just pushing the notation, I mean, one more dimension. All right, so the word is just the same, but you will see it's getting more and more complicated. Now, in a way, this kind of expression is fairly is already considered to be quite easy to do the integration. All right, so you can work it out directly, but for linear functions, we can use the theorem that follows. So either you take it as this is, or you work out expectation of x plus expectation of y. But bear in mind that x and y are coming from a joint one, so you will have to do it. Okay, let me proceed and see whether this example will be, work out closer. All right, so theorem 3. Okay, if you want to remember this theorem, you can put it in word like this, linearity of expectation. So the expectation operation is linear. So meaning that you can always move in and out of the constants, all right? So this is how, so we can do it term by term. So actually, if you do it in slow motion, it would be term by term, so it would be expectation of A0, expectation of A1, x1, plus and then expectation of AN times XN bracket. And now, because of the constants, you can always pull it out. So this will be the final expressions here.
Professor?
Yes?
So would that, like, x1 through xn, would those be the marginal distributions of x1 and x2 within the joint distribution?
Good question. Actually, you will, if you know the marginal, then you can directly use the marginal. If you don't know the if you haven't calculated the marginal yet, you will be forced to do it. Let me illustrate this. Yeah, it's a good question here. Let's only work on okay. Let's say we only have two dimension joint distribution. So again, we will have this. So the setting is x and y are jointly distributed. We assume it is continuous just to work out the calculations. So to calculate the expectation of x, you have two choices. Either you do it according to the marginal of x. But if this is not available to you, then you have to go back and work out this. All right. So if I regroup it again, okay. Of course, the order integration is again you can interchange. So basically, you can either use this directly. But usually, if it is a jointly distributed situations, the marginals are not given to you yet. If they are kinder, they will ask you to calculate the marginal. But this is only in the exam setting or in homework setting. I mean, if all you are interested in this, it's not a homework problem, then you can use this context. All right. But in the meantime, when you integrate y first, you actually calculated this. All right. So, of course, you don't need to do it this way, or you can do it dx dy. Then you are not calculating the marginal. So, but you are using the joint PDF. So, yeah. Yeah, but this is a very good question because it illustrates that you really understand at least the problem because originally they are jointly distributed. But now I only have one single of them. So you can see it in both ways. Either it in terms of integration, then if you only have if you have the marginal of x1, then you are doing one-dimensional integration. But if you only have the joint, then your integrand will be small x1 times the joint density function, and then you have to integrate n dimensions, all right? Now, you might think that, how come the second one is much harder in n dimension when you're doing But you have already done it if you found the marginal, because in the marginal you actually do n-1 dimension integration. I mean, it's already done. And that is how you get the marginal, right? And so when you only using the marginal, you have to still do one more integration. So in the end, you still do n integrations. So it's the same problem, all right? Okay, now this is the interesting thing. Expectation of x is a constant. So we use mu. Mu usually stands for the mean, and then the subscript x, uppercase, refers to the mean that comes from x itself, and this. Now, for this particular function, which is the product of the two, will be led to the definition of covariance. Let me give you some ideas why this is a good summary statistics of sort of like correlations. Now, in a lot of situations, correlations, you think of it as positive correlation, means bigger X tends to have a bigger Y. For example, if I look at age and shoe size, if you're older, your shoe size is bigger. There is this tendency, right? Now, this is, of course, very correlated, okay? But let's say, in general, say, looking at the height of the spouse, usually taller husband have a taller wife, or the other way around. So, but it's not always the same. It's not always the case, all right? So, so if you plot, this is the height of husband, and then the height. Now, of course, we don't have negative value. I mean, so that is not possible. All right. So there is a tendency that it is somewhat like here, the points, right? So what do? They first have, this is the mu of y, and this is the mu of x. And so if you have the height for this particular couple, then the difference here will be the y value minus the mu of y. That is, I mean, for this particular couple, the wife is taller than the average of the woman among the wives. And then this will be the difference of, I mean, the amount taller of the husband than from all the husbands, all right? So here. Now, if this point here, the product of these two number, which is the gxy over in your slide, will be positive. And if you pick a point here, both values will be negative. And so again, the product would be positive. And whereas here, if you pick a point here, one is positive, one is negative. And so when you do this, so basically, if you think that the things are positively correlated, it would be somewhat like the forward slash, this kind of situations. And so there is more of this positive products than more of these negative products. So as a result, when you add them up, so there is I mean, basically it's positive. So they are summarizing this kind of situations in one single number, meaning that there are more points or more weights that you lie on this kind of diagonal than on along here. So as long as the points lie in the first quadrant and the third quadrant, the product, the expression is positive, and then the second and the fourth would be negative. The expectation is just summing them up and then take average. So it's still basically summations, adding things up. So if you have a lot on the first and the third quadrant, it would outdo the second and the fourth. So the remaining balance would be positive. So that is the whole idea of doing this, all right? So this is a highly reductive thing. You summarize the pictures that I just draw, the cloud of points, into one number. okay, and that is nowadays called, later on will be called Pearson correlation coefficient later on, all right? So now, of course, this can be very misleading because you summarize a picture into one number, all right? Now, during our days, when I was a student like you, plotting things are really using pen and paper. So we try not to plot things. And actually, we try not to do calculations. But anyway, nowadays, doing all this can be done by Excel or software. So the best thing is not only just calculate the correlation coefficient, which is a single number, but do the plot too. Ask the software to do so that you actually see it, okay? All right, so this is the definition. So I pick a particular function in this form. The excess over its own mean, and the excess of the other variable over its corresponding mean. Okay, if the tendency that this is bigger than mu x, if they are positively correlated, then the other variable will also tend to be bigger than her own cohort, all right? So, so as a result, the product is positive. And if the man is less than the mean of the cohort, and if the wife is also highly correlated with in a positive way with the man, with the husband, then she will also tend to be shorter than the cohort. So again, this will be negative. So majority of the situation, this will be positive, all right, and so on. Now this is how we argue from this. But if everything is summarized in one single number, we lost track of actually how the numbers cancel one another. But it still gives us an indication, all right? It just suggests it, all right? Do you get my point? I mean, if I know the individual number, I know whether it is a lot of positive things or a lot of negative things, right? And even by how much. But if I only give you the sum, by looking at the sum is positive, I know they are more likely to have more positive things, or some of the terms must be very large in order to compensate the cancellations of the others. So my picture is not very clear now because I summarize everything in one number, but it still is suggestive. So this is what we call covariance, measuring how the random variables are correlated to one another. Okay. Now, properties of covariance, it is in a way, this is a very useful formula, part A, because you can have a choice of either calculating the covariance by its definition. Now, back in my old days, because we usually do it by hand, what it means is we have to subtract the number for every number by this mean. And I also have to do it. So basically, I have to do many subtractions and then do the product. Whereas here, I only do one subtractions finally. Okay, so this is only when you're doing it by hand, you appreciate the difference. But of course, the drawback of this is very often, if you are doing this, there's a tendency that x times y tend to be big. So as a result, you're dealing with big numbers. Okay. Whereas here, the number tend to be smaller because you have subtractions, so you have some cancellation. So you are dealing with some smaller numbers. So, but this is immaterial nowadays because I don't think you are going to do it by hand. But this is a very useful thing. All right. The covariance of x and x is actually the variance of x. Now this is very useful. So variance of x is actually coming from a special case of covariance, the covariance of x with itself. The covariance, this you can summarize it in one word. The covariance is symmetric function in the random variable. So you can either xy or yx, doesn't really matter. Okay, now the Part D, I want to highlight this. Whenever you change your origin, basically when you add B, you change your 0 for X. And when you add D here, you change your origin of the Y. The A and C is just a scaling factor, all right? So the scaling factor survives, but the choice of the origin, B and D, will be 0. It is because the definition here, it would be moved by B amount here, but the expectation will also be moved by another B amount. So it is actually cancelled right here. Is that all right here? If you change it to AX plus B, then, so this would be AX plus B. And this would be expectation of AX plus B. So the 2B will be cancelled here. And the D will also be cancelled. All right? So whatever you translate, because you are translating everything by the same amount, it will disappear. Just like invariance. All right? Okay, see, but the fact that you are using different unit will come out, all right? So A times C. Okay, now we have the variance of AX plus BY equal to this. Maybe I choose a specific A and B because in itself it is also interesting. This would be the variance of X plus the variance of Y plus 2 times the covariance of XY. Okay, so if you are able to calculate, so basically you have 4 quantities related in one equation. So if you have 3 quantities that you know, then of course you can calculate the other one. So the emphasis of part E is saying that this is the quantity that we are interested. Okay, so that's why we want to compute this. But suppose you are interested in the covariance, but somehow you know the variance of the sum, and this is this, all right? Now this is actually, I don't know whether you have learned these things in your trigonometry class. This is what we call the cosine rule. All right, so something like this. This is the square root of the variance of X, and then this is the square root of the variance of Y, and then this is the square root of the variance of X plus Y. And if this is not a right angle triangle, there is an angle here. And by a suitable choice of it, this is actually corresponds to your usual right? So this is your, cosine rule for your triangle things. But if you haven't encountered this, it's okay. But there is a parallel here. And actually, in higher statistics, people define the angle between 2 random variables, okay, as a measure of this. When the angle is 90 degrees, it corresponds to independence. All right. So people are giving a geometric meaning to it, but as a first module, you don't quite need it. Okay, if X and Y are independent, then the covariance is 0. This is important. I don't know whether we have a proof. The proof is very straightforward, all right? Okay, so if X and Y are independent, then the covariance of xy equal to 0. Now, first of all, I want to emphasize that this implication is only one way. The converse, meaning that if the covariance is 0, it may not imply x and y are independent. Now, yes. Yeah, sorry. If x and y are independent, the covariance is 0. And if you only know that the covariance is 0, you cannot say that x and y are independent. The reason is the following. To show that x and y are independent, you actually have to check all the joint density equal to the product of marginal for every x and y. Now, this is a requirement much severe than just looking at one number summary. Okay, so it would be too much to expect a one number summary captured the behavior of the how the joint density is equal to the product of the. Okay, so I'm going to show it why this is the case. So this is by definition. All right, and so this is if I'm in the discrete setting. So I would have small x, small y, x minus mu x, y minus mu y, times the joint probability mass function. So far I haven't used anything yet, but now here I use the fact that they are independent. If they are independent, their joint density come from the product of their marginals. And so now I group this together and then group this together. So I can rewrite this as this. All right? And so if you look at this a little bit closer, this is just expectation of x minus mu x, and this is expectation of y minus mu y. All right? And so as a result, the expectation is linear, so it would be equal to expectation of x minus its mean, so which is 0. So both of them are 0. All right? So the covariance would be 0. So this is an important result. If I know, which I know a lot here, the fact that they are independent, then the covariance is 0. Now this is usually not cast in this way because there is another quantity we are going to introduce is the correlation coefficient. But the correlation coefficient is basically the covariance divided by something. So if the covariance is 0, the correlation will be 0. All right? So that is where we will talk about. Note that the converse is not true. That is, two random variables with 0 covariance are not necessarily independent. Okay? Okay, an example. A simple example of two dependent random variables x and y having 0 covariance is obtained by letting x be a random variable, and then y is something that is a function of x. All right? So definitely, if you know x, then you know y, right? So x and y can't be independent. Okay? We will verify in a moment. Now, the idea of having this is because this probability mass function is symmetric at 0 because it is minus 1, 0, and 1, and they put mass 1/3. So it is symmetric at 0. Now, if it is symmetric at 0, the expectation of x cubed would be the same as expectation of minus x to the power 3. And so as a result, you should be able to prove that this has to be 0. So this is just a very concrete counterexample, but we can give a more general counterexample. So as a result, the covariance of xy is just equal to this. This is part A in the property of the covariance. All right? And so now I plug in what y is. Y is x squared, so I have expectation of x cubed for my first term. I don't need to calculate the expectation of y because expectation of x equal to 0, so the product would be 0. So in fact, if you don't want to do unnecessary extra work. You don't need to compute this, all right? So because this is 0, and this is also 0, so the covariance would be 0. And then clearly x and y are independent, because once you know x, I can tell you what y is, all right? In a very certain manner. Okay, now this is the thing that people used. So this is called correlation coefficients. There are many correlation coefficients. So, but this is the most common one. And then when you say it, most people will think of this. But if you want to be extra clear, then this is called Pearson correlation coefficients. Pearson, P-E-A-R-S-O-N. Pearson actually is a father and son. Both of them are very famous statisticians. I think one is a father, Egon, and then the other one is Carl. So if I remember it correctly, this is the father, this is the son. But you can Google it to verify it. I think you learned in your statistics, I don't know whether you learned about Neyman-Pearson lemma. Neyman-Pearson is the younger Pearson. Okay. If you have heard about Fisher, both three of them are almost like founders of statistics, and all of them have very strong personality. There is another guy called Neyman. I think it's Polish by race, Jerzy Neyman. I think Jerzy Neyman, give you some gossip here. It was in the probably in the 40s, late 40s. Jerzy Neyman actually worked in UK. All these people are, came from, they established a career in, the UK university. One of them is University College London. Very famous in statistics at that time. Fisher can't get along with Neyman, and Fisher is much more senior and very powerful. So he told Neyman, stay as far away from me as possible. Then Jerzy Neyman went to Berkeley, and he started the Berkeley Department of Statistics. So it might be good for American statistic development, but the early founders are all very, they are very eminent statisticians, but they also have very strong personality, strong in the negative sense. All right. So this is the definition. Now, one thing I want to emphasize, another thing is this correlation coefficient does not depend on the unit of measurement. So this is dimensionless. Now, let's go back to the covariance. All right. If the x, let's say, we are interested in the, say, weight and height. Suppose x is the height of a person, and then y is the weight of a person. Now, it depends on which unit you measure. If you measure x in kilogram, and then height in meter, so the unit would be kilogram meter. All right? Now, but the covariance can be very much depending on your unit. Suppose I use gram for my weight, which is rare, and then I use centimeter. So the difference would be 100,000 times the number itself. Okay? It is because you are using centimeter gram unit. So the 100,000 times of the other number, might give you the impression that they are very correlated, but it is just because of the unit. So that is why they wanted to correct it back by having a unitless kind of measurement. All right. So if x is in meter, then the variance of x will be in meters square. After the square root, it will still be in meter. So the dimension meter will be cancelled out. And then for y, if it is in kilogram, the variance of y will be kilogram square. So after the square root, the kilogram will also be cancelled out. So rho xy is an absolute number. Okay, does not depend on the unit of measurements. Later we will also have another thing that this number is always between -1 and 1. All right. Okay, it's stated here. This is because of some kind of inequality. The inequality is what we call Cauchy-Schwarz inequality. We are not going to talk about that, but this is a nice thing. First of all, this number is unionist, and then also is always between -1 and 1. So when it is very close to 1, I have some kind of an interpretation. X and Y are very correlated, and then it is in these directions. When x increases, y will also increase. But when it is close to -1, when x increases, it will lead to a decrease of the other one. All right, so now in a lot of science, especially maybe even in engineering, when you're doing control, you want this kind of things to happen. If you increase your x, you might want to increase the other y. So if they are highly correlated, by changing the x, you will have an effect on y. But say, for example, if you increase, say, some protein level, and if it decreases the protein production for tumor, so this is a good thing. So it is negatively correlated. So when you increase one thing, you will suppress the other one. In our body, a lot of proteins are doing this kind of controlling one another by having this kind of situation. So rho xy is a measure of the linear relationship. So it does not measure this. We will we'll see some examples. It's only measuring linear. So if you have the correlation, something like a circle, when you do your calculations, the correlation coefficient will be 0. But you know that they are highly correlated. But it is correlated with a quadratic relationship. So this is only for linear. Now if x and y are independent, then the rho xy equal to 0. Okay, because rho xy is actually equal to the ratio of this. Coming from the previous slide, that if x and y are independent, then the covariance is 0. So what it means is now the numerator here is 0. So as a result, the correlation is 0. Okay, in fact, here if the covariance is 0, then the correlation is 0. The converse is also true. If the correlation is 0, then the covariance will be 0 because they are connected by these expressions. Okay, this is reiterating what we have said. If x and y are independent, earlier we know that the covariance is 0, but we can now phrase it in terms of the correlations. Okay, it's equal to 0. Now, we wanted to emphasize that this is referring to the pair x and y. So if you have more than two variables in consideration, then you have to tell people which pair you are using, or which pair you are working on. So this is this. Now the converse is not true. Okay. Okay, so usually this is, people have another way of saying it. So either people use correlations, or some people call the term associations. So here, if we just summarize it in keywords, independence implies independent, uncorrelated. Okay, but this is not true. All right, so the converse is not true. This is a very serious mistake if you commit this, all right? So it's like cardinal sin. Okay, so we have this. So now we have this thing, and now once we have a table, then it is fairly straightforward to do the calculations. So this. All right, so let's do A. So we are using the property of covariance, the property A. So I found the expectation of the product first. And so you just have to do it, all right? So I think if you have a table, nowadays if you key everything in Excel, Excel can do a very good job for you rather than this, because it is very prone to make mistake if you do it by hand. So this is equal to 1. And then when you work this out, this is half, this is 3 halves. So as a result, this covariance is 1/4. So what it means is now you have a mental picture. Generally, when X is bigger than its mean, and Y is bigger than its mean, then they are clustering around the first quadrant and the third quadrant. If you really want to plot the points, you will see you have 0, 1, 0, 1, 2, 3. And then now the center of X is 1/2, and the center here is 3/4. So you will be able to see where the numbers are lying on the first quadrant with respect to the mean of the two means, or in the third quadrant. Okay, so we found this. And now find the expectation here. You can do it this way, or you can do it in a linear way, expectation of Y minus expectation of X. Now here, because of this is the original table, but now since it is very easy to work out the marginal, once you have this original table, then you can work with this. All right, to calculate the expectation of Y. But if you skip this step, then this would be what you need to do, something like this. This will be what you need to do here. So, all right. Okay, the variance of X. Now we are also using the same thing, expectation of X squared minus the square of the expectation. So this has been found earlier, and so this is 1/4 and this is 3/4. And so as a result, the correlation coefficient is 1/√3. You know, at least if you get a negative sign here, then something is wrong, because earlier we know the covariance is positive. So the sign of the correlation coefficient is depending on the sign of the covariance, because the denominator is basically always positive. All right? Okay. So to calculate this, then you have to find out the marginal in X equal to 1. So you have to find out the specific row total. And then you have to renormalize it so that you get this, and then you get this. All right? Okay, so maybe I think I'll stop here. Okay, so I'll see you tomorrow in the multi-purpose sports hall. It's not a sports game, but okay. All right. Okay, for the seating plan, I think Dr. Chan is working on it. The delay is because we have a number of combinations. Many of you are taking this test on its own, tomorrow. But then there are quite a number of students have a test before, or some have a test afterward. So we are going to, there are only 3 entry points, so you will be allowed, the bulk of the people will be allowed to enter the hall. The test will start at 10 and end at 11 for, almost like 95% of the people here. And you will be sitting in the hall. There are 2 sections, Section A and Section B. Most of you will be sitting in Section A. You will be given a seat number, all right? And then for those who have to take the test earlier or later, we put them in Section B. But Section A is probably not enough. We have only about 440 seats, or 420. So some of the students taking the test from 10 to 11 might have to be seated there. So, the arrangement is the following. If you have notified us earlier enough, we will put you in the right sections. So you just go back to the seat. We will put up the seating plan in the Luminous, as well as just outside the hall, so you can familiarize yourself with it. And if we accidentally assign you, suppose you want to start early, 9:45, but we haven't heard from you, we put you into the other one, then you still go back there, and then we will redirect you to sit with those who take the test early. All right.